So continuing on, we were talking about Lewis dot structures and shape of the molecules, and we introduced these 5 archetypical shapes that make up the molecules that we see. But those were all simple cases where all of the atoms were the same, or approximately the same. So a good example of this would be something like CH4. We could draw the Lewis dot structure, and we see that the central carbon, 4 items around it, and we can look at this and we can see, oh, there's 4 electron regions. This has to be a tetrahedral geometry. But what about something like NH3? Okay, if we draw the Lewis dot structure for that, we'll get the following. NH3. Again, we see 4 electron regions, but we wouldn't describe this as tetrahedral. The electronic configuration suggests that it's tetrahedral, and associated with that would be the bond angles here. The bond angles should be about 109.5, and if you actually measure these in ammonia, you see that these are about 108. But we wouldn't describe this as a tetrahedron because we have this lone pair that sticks off into space. This is a structure that is described as a pyramidal structure, because if you actually look at the nitrogen, the hydrogen forms a series of, if I think of it as a little pyramid-like structure. But yet it's still based off the tetrahedron. If you take a look in your textbook, you'll see chapter figure 10.1 describes the geometries, the overall geometries, whereas figure table 10.2 will describe all of the individual shapes. If we take a look at water, we can again draw the Lewis dot structure for water using our steps described in previous, and we could see that this material also has 4 electron regions. The bond angles between these components are actually 107.5, change 107 degrees. And approximating the 109.5 that we see in the tetrahedral geometry, but we would describe this one as being bent. Because when we describe the shape, the individual shape of the molecules, we always just talk about the atoms we see, not electron regions. Though the electron regions directly give rise to the shape of the molecules. So all those have to be taken into account. And there's a nice little algorithm for discussing these in your textbook. But let's just take a look at a quick example. We'll take a look at SO2, which I believe we drew earlier. This is a good time to hit pause and draw the structure of SO2. Okay. So you hit pause. Yeah, sure you did. And so here's the Lewis dot structure of SO2. Following. Now, we can see that there are actually, around this central sulfur, there are 3 electron regions. We count the double bond as a single electron region, and so it would mimic the 3-electron region example that we had, which was a trigonal planar molecule. And so this bond angle between these oxygens, should be 120 degrees. But if we just take into account the molecule itself, the atoms themselves, we would describe this as a bent structure. And that directly gives rise to the properties of the molecule. So this one we would describe as bent. Now, it works for even more complex structures as well, such as Sf4. So now's a good time to hit the pause, try and discuss the geometry of the Sf4 molecule. There. So we add up there are 4 fluorines, 28 electrons, 6 electrons for the sulfur, to give us 34 electrons total. We draw a simple structure that connects all the sulfurs and all the atoms, sulfur to all the atoms, and then we distribute those electrons around the structure, leaving us with 26 electrons. We use 8 for the bonds, leaving us with 26 electrons to distribute. 1, 2, 3, 4, 5, 6. 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's 24 electrons, leaving us with a single pair of electrons localized on the sulfur. If we do a quick check, we see that all of our atoms have the correct number of valence electrons. The sulfur, though, actually has 10 valence electrons. But as I mentioned in one of the discrepancies in previous slides, that this is normal. Atoms can have 10, 12 valence electrons without any difficulty. Though for the lighter atoms like carbon, nitrogen, oxygen, fluorine, this is actually more rare, but still plausible for the heavier atoms. So we see that this has a 5 electron regions, and the question is, why? What sort of shape does it take? And looking back at our textbook, we'll see that this does what we call a seesaw, where the lone pair sticks out into space, and due to the fact that electrons take up space, they distort this molecule to create what we call a seesaw structure. Additionally, we know that this is based off a trigonal bipyramid. And because it is based off the trigonal bipyramid, we can even comment on the bond angles. We know that the bond angles between these fluorines would be 90 degrees, but between these it would be closer to 120. In fact, what we'd see is a slight compression expression of this. So now, notice we talked about earlier is how we actually see deviations from our bond angles. We see things like 109.5 as opposed to 109.5 for some structures, but 108 for others, 107 for others. And the reason for this is, we can simplify, is what we call Vesper. Vesper actually also describes the shape. Valence shell electron pair repulsion basically looks at how electrons interact with the atoms that are bound to it. And so for something like Sf4, why did we put the lone pair at this equatorial position as opposed to some other location on the molecule? And the answer is that electrons take up a lot of space, particularly non-bonding electrons. And so this lone pair is actually quite large and would require the most spacious area it can find. So these electrons take up a lot of space. And so one of the most important types of interactions are these electron-electron repulsions. And so these repulsions force the electrons to try to get as far away from one another as possible. And this is usually where we see lone pair interactions, trying to maximize the distance between the lone pairs, moving them into the most favorable arrangement that gets them as far away from one another as possible. This flattens them out. This is often why we can see things like Sf4 we can observe that Sf4 is actually a square planar molecule. You can prove that to yourself, because it tries to deviate, tries to move those lone pairs as far away as possible, and the only best way to do that is 180 degrees separation. So the electron-electron repulsion is one of the strongest, and then next comes the lone pair, bonding pair, and lastly bonding pair, or in other words atom-atom interactions. All right? So those are the hierarchy, with the electron-electron being probably the ones that most often dominate. And this is also why oxygen is 107 degrees, reports 107 degrees rather than 109.5. It's because these lone pairs on the oxygen are repelling each other, and they're also pushing on the hydrogens, trying to knock the hydrogens out of the way, contracting that bond distance. So many of the deviations you see in the bond angle are due to these types of interactions, and so be prepared to rationalize these deviations from the perfect geometry. Okay. So just to wrap up Vesper valence shell electron pair repulsion, well, that's what we're talking about. Practice drawing each of these structures. You should be able to draw each of these. We've already talked about 4 of them, but as practice, 3 of them, you should be able to draw all of them. All right. So you can also, you should be able to, at the end of this, you should be able to draw a structure, describe its geometry, the shape of the molecule. Again, not the electron-electron geometry, but the actual shape of the molecule. And you should be able to discuss the likely bond angles. The bond angles associated with the molecule. All right.